Hi everyone, so we'll be solving question 6. Let's take a look at the question first. It mentions here that you have a transverse wave. Transverse wave means by a wave where the particle's oscillation is perpendicular to the propagation of the wave. Perpendicular, that's why transverse, okay? Then this transverse wave is traveling along a stretched string and it travels with a speed of 80 meter per second and a frequency of 200 Hz. Let's just copy this thing down. Speed is 80 meter per second. Then the frequency is just 200 Hz. Okay, so we extract the information out. Next thing, the stationary waves are produced on the string. Well, then they suddenly mention you have stationary wave. They say you have a transverse wave which is traveling. So it's a traveling wave. It's a progressive wave. Then suddenly they tell you a stationary wave is being produced. So how do you produce a stationary waves out of nowhere? Okay, to know this, let's look at this video over here. Okay, so the question just now mentions that you have a stretched string. So when you have a stretched string, it means by the string will have to be fixed at one end. Only you are able to stretch it, right? So you can think of a straight line, a string, then with one end being fixed. Okay, so if you have something like this, if you try to send a wave through this string, this is what would happen. Notice if I send a wave pulse, see what happened? Something will be reflected back. Okay, before that, it's okay. Let's see. Okay, you can see the wave is being reflected back after it reached the other end. So it means by if I send a wave that looks something like this through to the fixed end, I send a wave something like this, what will happen when it reaches this end? We call this end the boundary. Once it reaches this end, you see a similar shape wave being reflected back. Okay, this one is reflected on the opposite side, but that's not our concern. What we need to know is that it's reflecting back with the same velocity. Okay, so we call this one the incident, whereas we call the reflected one the reflected wave. So if you have a stretched string, you send a wave pulse, and it reaches the end of the string, then the same shape of wave pulse will be reflected back towards your hand. Okay, so this is what will happen if you have a string which is fixed at one end. So now if you look back to the question say it's a traveling wave. It's a transverse wave. So means by it's not just a single wave pulse only. It's a continuous wave. So what will happen if you send a continuous wave then? So let's say you send a wave that looks something like this to the one end. What will happen is a wave of similar shape will be reflected back. Okay, we are still applying the same principle here. Okay, so the same shape will be coming back. Okay, so again, this is the incident and this is the reflected wave. So because these two things are overlapping with each other, then you have to sum up these two things. Sum up using what? You sum up using your principle of superposition of wave. Okay, what does principle of superposition of wave tells you? Well, it tells you the resultant displacement is just the linear summation of the incident and the reflected wave. So means by if this is 1 and this is 2, then your y resultant will just be y1 plus y2. So what will y1 plus y2 be? Let's try and simulate it on Desmos. So here we are in Desmos. So I have written down a series of equations, but don't worry, it's not too complex. I'll go through it one by one. So just now we say we send a traveling wave from one end to the other end and let it reflect it back. So let's say we have our first equation here, which is just a traveling wave equation that we learned from the previous subtopic. So we have a traveling wave, and because it's negative here, it's moving to the right. Okay, it should be moving to the right, just like this. Okay, so since it's moving to the right, and if there's an fixed point at the end, means by there will be a wave traveling back in the left direction. So you have another wave which is traveling back towards the left. So you have the red color wave moving to the right and the green color reflective wave moving to the left. So these two waves are happening at the same time on the same stretch string. You have a wave moving to the right and you have a wave moving to the left, both happening at the same time. So when they are happening at the same time, they are overlapping in the same region. They are overlapping on the same string. So we call this phenomena interference of wave. Two or more waves overlap in the same region. So when that occurs, how do you determine what's the resultant shape of the wave? Because of these two individual waves, we can find the resultant shape by adding the displacement up. Okay, why can you just directly add the displacement? Because of the principle of superposition of wave. Principle of superposition of wave tells you that if you have two individual waves overlapping in one region, you can find the resultant displacement just by summing the individual displacement. So this is what we will do. Okay, so this is my displacement for wave 1, this is my displacement for wave 2. So resultant displacement, I will just add up displacement for wave 1 and displacement for wave 2. Okay, sorry, displacement for wave 1 and displacement for wave 2. Then this one will be our resultant. So let's see what's the shape of this thing. Okay, I'll click. Let me move this a bit bigger. Okay, so let's see what would happen when we press play. Okay, do you notice what's happening? You have a wave, the purple wave, which is not moving to the left or not moving to the right. Let me remove the green and the red color. So now you can see clearly you have a wave which is not traveling. It is stationary. It is oscillating at its own place. So we call this kind of wave stationary wave. Not traveling to the left, not progressing to the right. It's stationary. It's oscillating at its own place. It's standing wave because it's standing. It's not traveling. Okay, so we call this either a stationary wave or a standing wave. Okay, so this is the pattern of, this is how a standing wave or stationary wave looks like. Okay, so you might be wondering, so what is the exact equation to represent this standing wave? Well, I'll introduce how you work through the summation for wave number 1 and wave number 2, but the result of your summation will be this equation over here at my cursor, 2a cos kx sine omega t. This should be the shape of the resultant wave. If you don't believe it, let's prove it. How do I prove it? I switch this on, then you see it will overlap with the previous wave. I switch this off, and I switch this on, then you see it's exactly overlapping on the big Y plus big Z. Okay, so it proved that this is the correct equation. This equation is equals to summing up this big Y and big Z. So this is the equation for standing wave. Okay, and since this is the equation for standing wave, how is it relevant? How do I usually analyze this equation is, I look at the front part first. The front part is 2a cos x. 2a cos x here actually represents the amplitude of all the particles along the wave. What do I mean is, let's say I switch this on. Okay, what you can see here is this red line here represents the amplitude for all the particles along the wave. Let's say if you are at this position 4, at 4 here, you are at this position, this will be your amplitude. So you'll be oscillating within this place. Okay, you'll be oscillating like my cursor do. If you, let's say you are at let's say here, this is 4.5. Let's say you are at 4.5, which is where my cursor at. It means by your particle over here will be oscillating with this amplitude. This rate here will be my amplitude, so you'll be oscillating around this place. Okay, if let's say you are at this one is 4.75. If you are at 4.75, the rate is here. So means by this is your amplitude. Your amplitude is 0. You won't be moving at all. So let's try to see whether it's true or not. Let's press play. As you can see, if I add 4, I'm oscillating within this amplitude. If I add 4.5, I also oscillate within this amplitude. But if I'm at 4.75, basically I'm not moving. The particle at 4.75 is not moving. Okay, so the equation 2a cos x here actually represents the amplitude of every single point along the wave. So if this equation represents the amplitude of different points along the wave, we can probably try to identify where is the antinode and the nodes of this standing wave. So what's the meaning of antinode? It represents the maximum amplitude. Okay, basically antinode means the position where the amplitude is maximum. So where is the maximum amplitude? You'll be here, you'll be here, you'll be here, you'll be here, 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 here. So you can see the position at 2 is an antinode. The position at 2.5 is an antinode. The position at 3 is an antinode. The position at 3.5 is an antinode. 4, 4.5, 5, all these are antinodes because the amplitude is maximum at these points. So these are all antinodes. So how about nodes? For nodes, it is stationary. The particle at the nodes will not be moving. So the amplitude will be 0. So these points like this will be nodes. So you can see that 2.25, 2.75, 3.25, 3.75, 4.25, 4.75. These positions will be the position of the nodes. Okay, so let's try to determine the distance between the antinode. Let's say this antinode and the next antinode is here. So what is the distance between this antinode and this antinode? You can see the distance is for here is 1 square here. Okay, so 1 square here is actually, if you notice, it's half of the oscillation, half of a oscillation of a complete oscillation of a standing wave. So this is a complete oscillation of a standing wave. And the distance between one antinode and the next antinode is the distance for half of the oscillation of the standing wave. Half of the oscillation. That's why if you are able to determine the wavelength of the standing wave, which you can get from the k here, you get lambda by 2 pi over k. That wavelength, if you divide by 2, lambda divided by 2, that will be the distance between the antinode and the next antinode. Okay, half of the wavelength. From one antinode to next antinode, the distance is half of the wavelength. How about the node? You can see the distance is the same as well, because in between every antinode, in between two antinodes, there's always a node in between. So the distance between the node is also lambda over 2. You can see it's basically half of the oscillation. This is 1 plus 1, 2. This is 1 plus 1, 2. So this one is half of an oscillation of a complete oscillation. Okay, that's why if they ask for the distance between antinode, is lambda over 2. If they ask for the distance between the nodes, is lambda over 2 as well. Okay, so this is fixed. It won't change. So knowing how a standing wave works and knowing where's the position and the distance between nodes and antinodes, let's move back to the question. Okay, so let's look back at the question. The question says you have a transverse wave, and this transverse wave is traveling along the stretch spring. Then you have your speed, you have your frequency, which I have extracted down here. Then from there, they say this transverse wave will produce a stationary wave. So they didn't mention how, and I explained how is because it travels, it reached one end, then it reflected back. The incident and the reflected wave overlap, and their interference, result of the interference will be a stationary wave. Okay, so now they ask us to determine the distance between two consecutive nodes. Well, we learned from the previous video, not the previous video, I mean the previous Desmos demonstration, where two consecutive nodes, the distance is just half of the wavelength of the standing wave. Half of the wavelength of the standing wave, and it's the same thing for two consecutive antinodes. Consecutive means by side, so it means by this node and the next node, not the node after next node, the node right after this node. Consecutive, continuous. Okay, so we say the distance between two consecutive nodes. I usually just represent it with 2n, one node and another node. Okay, so the distance will be half of the wavelength of the standing wave, what we discussed in the Desmos earlier. So how do we get the wavelength? Wavelength, you know it's V equals to F lambda. You can use this, so it's just half. Then the lambda will be V over F. Okay, then now it's a matter of substitution. So substitute your speed to be 80, your frequency to be 200. You do a bit of simplification. Divide by 4 become 2, divide by 4 become 5. This one, then you become 1 over 5 at last. 1 over 5 is just 0.2 meter. Okay, so what does this mean is, let's say this is your standing wave. I'm drawing just a portion of the standing wave that you see just now. Okay, so if this is a portion of the standing wave, so my node is 0 amplitude here and here. So I can say this distance here is lambda over 2. And the lambda over 2 is equals to 0.2 meter. Okay, this is the distance between one node and another node. Okay, so now let's look at question B. The question B asks for the distance between a node and an antinode nearest to it. So where is this position? You can think of it as being, okay, let's pick the same node as just now. This node I label it with yellow. So yellow not very clear, probably pink. Okay, so this node, the antinode nearest to it, well, we can pick this. This is also an antinode because antinode is maximum amplitude. So here can be antinode, here can be antinode. Okay, whereas, okay, I just label everything. So the node is here, the node is here. So now I'm looking for the distance between this and this. I think it's quite obvious. You can see that it's just half of the distance between the two nodes. So D between N and A will probably be half of D of N and N. It's half of this thing over here. So you take a half means by lambda over 4 actually. So it's just lambda over 4. But let's do it slowly. So in our answer here, you can say the distance between the node and the antinode is just distance between two nodes divided by 2. So you know it's 0 0.2. Copy it from here. Divide by 2. Then you get 0 0.1 meter. So what does it mean is this place it's 0 0.1 meter. And this is the distance between node and the nearest antinode. Okay, so I hope this simple diagram here can help you understand what are the distance you are looking for. So that's all for question 6. Thank you very much.